Hi everybody. My name is Anup Ghadge. I work at Salesforce, and I don't know if you know, but like we are a huge consumer of open source software, and specifically, I'm here to talk about some of the things that we've done, working with the community and kind of back and forth with Apache Bookkeeper, specifically around the scaling strategies for Apache Bookkeeper. So originally this talk was going to be me, JV, who's our architect, and Sushant as well. But unfortunately, JV and Sushant couldn't make it, but I'm here, so that's 1 out of 3. So before we go ahead, I'll just kind of walk you over the agenda of what I'm planning to speak about today, right? So we'll go over the introduction of Apache Bookkeeper. For those of you who might not know about it, you might have just heard of it as the storage engine for Pulsar or the name node engine for HDFS and things like that. But what does it mean in terms of our use case for Salesforce? That is the second part of the talk, right? And then as we scaled our use case for Apache Bookkeeper, we went from storage realms of terabytes to petabytes. And that obviously led to a lot of issues in terms of scaling. And I think the learnings there are something that everybody can share irrespective of the fact whether they use Bookkeeper or not. And then finally, we'll kind of go into some little details about how we made it work, right? So for those of you who don't know about Bookkeeper, I'll just give a very quick refresh. This is a highly technical talk, so basically the Bookkeeper storage consists of ledgers. Ledgers are like the blobs of store that we do, and the smallest immutable aspect of a ledger is an entry. And the entries are striped across different bookies, and the ledgers themselves have 3 main properties. One is the ensemble, that is how many bookies should the ledger be written to. The write quorum and act quorum decide the number of replicas and the minimum number of acts required to satisfy a write or a read, right? So one of the main reasons that we chose Apache Bookkeeper is because it is highly consistent, available, and durable. It's also immutable and append-only, which really matches our use case. The bookies themselves are really sort of dumb in a way. They just store stuff, right? Majority of the logic is in the client, which makes it a thick client, which makes us elegant to plug and play new policies. And you can spawn as many bookies as you want and kill down as many bookies as you want. They provide low latency reads and writes, which is great because of the quorum-based mechanisms. And the storage is organized in entries and ledgers is something that I've already spoken about, right? So our use cases were mainly just we needed immutable data to be durable and available, easy to operate and scale out at massive levels. So that's where the kind of dumb bookie situation comes into play, where you can just spin up more bookies without having to worry about do they need to have any state or not. And all of this can obviously be run on commodity hardware, so public cloud providers, so you can just scale up and scale down as per your requirement. However, once we started with these deployments, we noticed that our data footprint started to really increase. And once they start to move to a scale of 1 petabyte, the traditional Bookkeeper architecture, which is being used by Pulsar and other users of Bookkeeper, started to really break down. And that's where we had to kind of really revisit the way that we were using Bookkeeper specifically. So I think the earlier talk also mentioned about ZooKeeper and how they've provided different ways to move away from ZooKeeper, how they've provided new ways to move away from Bookkeeper with S3 and cloud storage, etc. So you'll see something similar here that we've done. I believe this is sort of a trend which I've seen across different companies as well, that where people want to leverage the maturity and security of object stores like S3 and Google Cloud Storage and different kinds of storage engines. And also people are trying to move away from centralized points of failure or centralized metadata stores like ZooKeeper. So in terms of Bookkeeper specifically, the metadata service, which is ZooKeeper in the most traditional sense as you know, stores information for service discovery and ledger metadata. So service discovery meaning like, something like cookies where every bookie registers itself with ZooKeeper to say that, I'm here. So whenever the client needs to pick bookies to write, it knows where to go to create the ensemble. And it also stores things like the ledger metadata, which is actual metadata about the ledgers, which is quite large compared to something like cookies. You have many details regarding the ledger here as well. Something that I've not shown here, which is actually very prevalent, is the segments in the ledger metadata. So for example, when you create a particular ledger, you get a certain ensemble, and then over time, those AWS instances would go away, or you would decommission the bookies and you would replace them with new bookies, things like that, and you get a new ensemble. So this chain of different ensembles is called a segment, and that is also stored, which also gets really big. So it might not be very obvious, but the ledger metadata which you're showing here is actually quite big. And it gets even crazier when you start to go to the petabyte level. So let's just assume that we have 1 million ledgers, right, which translate to around 5 million Z nodes. So those of you who don't know, like, the metadata tree which is stored in ZooKeeper in form of Z nodes is cut up in terms of the ledger ID itself, and that way you get like a nice tree format with log n complexity to look for your particular ledger. But even when you do it with 1 million ledgers, it turns into like 5 million Z nodes. And when you try to have such a setup, it affects the ZooKeeper CPU, it affects the create latencies, and it affects even the stat and close latencies, which is really crazy because the whole point of going to ZooKeeper is you want that to be extremely fast and extremely instant. So at scale, managing this ledger metadata becomes a problem because we rely on ZooKeeper for not only the registration, service discovery, ledger metadata, but many of the traditional bookkeeper processes, the internal processes, depend on scanning the entire metadata tree, as I said before. So these things are called deep scans. These are something that can affect when there's data loss on a bookie node, when it is backed by an object store, or if you want to decommission a particular bookie node, or you want to list ledgers by a client, right? Like, let me just explain each one of these. So you have the entire ledger metadata stored in ZooKeeper in form of 5 million Z nodes in a big ZooKeeper tree. A particular bookie just randomly goes down, right? As I said before, the bookie software itself doesn't know what it owns on that node. You need to check in ZooKeeper, you need to check in the ZooKeeper metadata, you need to check that particular segment, you have to find a particular ensemble. And in order for you to know that, you have to scan the entire ZooKeeper metadata tree. That's a deep scan, right? Similar thing can be said when you want to plan decommissioning of a particular node, right? And of course, if you want a client to simply list all the ledgers, that will also involve scanning the entire tree. And with 5 million Z nodes, it gets a little more intense, right? There's also this thing about garbage collection on bookies. So over time, if a particular ledger is deleted, it's kind of garbage collected, and the garbage collection also needs to know that, which ledger am I holding and which ledgers have been deleted. And the central source of truth is, of course, ZooKeeper. So you go to ZooKeeper, you scan the whole thing, and you say that, oh, this ledger is missing, so why am I holding it? I should just delete it, right? This is obviously done at a much slower cadence. This is all configurable anyway, right? But the deep scans get extremely intense when we go to this 5 million Z node level. So let's take a look at a typical ZooKeeper deployment and see how it gets affected with these deep scans, right? So a traditional ZooKeeper instance type could be an M5 X large, speaking in AWS terms, right? An ensemble of 5 ZooKeeper servers, each having 4 vCPU. A single bookie node doing a get children call, because internally when you look at, if you kind of step through the code, you'll see that it kind of translates into get children calls, right? And if you keep it an async API, no rate limiter, like, no holds barred, how much time will it take? So for like 1 million ledgers, it takes about 45 minutes, and it pushes the CPU of ZooKeeper up to 85%. Now, say you have an ensemble of 10 bookies. 10 bookies doing the same thing with an async API, no rate limiter, doing deep scans, right? Every 10 bookies have been configured to garbage collect once a day, right? So at like 12 p.m. or 12 a.m. in the night, all of them come online and start to garbage collect, and they do get children calls, right? With no rate limitation, what will happen, right? For 1 million ledgers, the CPU just shoots up to 99%, the async API starts to fail, and you've just kind of, lost it over there. So this is just an ensemble of 10 bookies, right? How can you scale even more than that? And how can you support a larger footprint if you can't do this? So in order to kind of just take another look at it, it looks like 1 petabyte of storage basically means 1 GB of a ledger, which is usually not what you see. They are even bigger. And if you say, okay, 1 GB per ledger, 1 million ledgers is 1 petabyte, right? That translates to these 5 million Z nodes, and all of these essential bookie operations like listing ledgers, deep scans, garbage collection, decommissioning, all of these things start to really, kill ZooKeeper over here. So you could say, okay, maybe I could, scale up my ZooKeeper node cluster node, right? Or maybe I could change the way that I'm storing the Z nodes. So instead of the traditional Z node tree, I could maybe use a hash table or something like that. Some different way of doing it, right? But is that really solving the problem is what we discussed. Because when we were solving this, we said that we want to get away from this, right? You might have seen it in the Kafka community with folks trying to move away from ZooKeeper. You might have seen it in the Pulsar community with, Akshay and all of these other things. We also wanted to kind of think about it deeply and see that, do we really need to, rearrange the chairs and tables on the Titanic, or should we move away from ZooKeeper as much as we can for some of these non-critical operations at the very least, right? So that's the idea. In order to move away from ZooKeeper, we wanted to understand which are the critical operations and which are the non-critical operations, and see if we can offload the non-critical ones to something like an object store. So here's something that we had to change. So the first thing was, if you look at the architecture, we had to kind of revisit the architecture of how we are deploying Bookkeeper. We separated the bookies into log store bookies and data store bookies. The log store bookies will be backed by EBS to support really fast read and write latencies, and data store bookies are backed by NVMe, and in general, the whole thing is backed by the object store. The object store here could be S3 or any other object store that you'd like. So these log store and data store bookies are pretty much the same bookie software, but they're running in different personas. By different personas, I mean, they will have different configurations, they'll run different scrutinies, but essentially it's the same software, right? Since the log store requirements are about latency, they are backed by EBS. The data store requirements are more about durability. They're backed by, in the short term, NVMe, and in the long term, by the object store. Now, if you take a look at the architecture, we have ZooKeeper on one end for the service discovery and metadata, and you have the Bookkeeper client talking to the log store and the data store for reads and writes of both. And then, of course, the object store. So the log ledgers get persisted. If I kind of walk you through the life cycle of these things, right? Say you're a bookie client, you want to write something to the log. You go to the log store, you write the ledgers, they get persisted on the EBS. For data store or data ledgers, the Bookkeeper client writes in parallel to the data store as well as the object store at the same time. And the data store bookies have the particular ledger at that time, but if for some reason, those bookies kind of don't have the data, they kind of rehydrate from the object store, which is like another scrutiny which runs, from time to time to understand what's there and what's not there. Obviously, if you look at the container perspective of these things, you'd still have the auto recovery or the auditor, as we call it, and then that would be in the data store as well, which will contribute to this. All right, so the scenarios which we need to support in this new architecture are, what if there's some data loss in a particular bookie, right? Or if there is an NVMe loss on that node. What if we want to decommission an entire bookie? And what if there are missing ledgers and the traditional operations which we went over, like garbage collection, listing ledgers, things like that. So if we zoom into it, and if we look at the container kind of perspective, right? We introduced this thing called the auditor, which is kind of already there in the traditional bookkeeper, in the bookkeeper open source community. But our auditor does very specific things for the data store, right? It won't run all the scrutinies that we run in the community bookkeeper. It will run probably, because there's no like replica stuff, it won't run like the replicas check, scrutinies and things like that. But we've got a new scrutiny which will kind of take a look at all the data which is stored in the data store in that particular bookie, convert it into a reverse map, and then process that to the object store as well at a bookie level. We'll go into the details over here, right? So a reverse map is basically, instead of storing that entire big tree in ZooKeeper, we store a map of bookie to ledger mappings, and we store that in S3 and we persist it there, and then incrementally we keep adding to it, right? That way, if there is NVMe loss or bookie loss or things like that, or if you want to decommission, you can simply just read that particular file from S3 and understand what ledgers belong to that particular bookie. And once you know those ledgers, you rehydrate them from S3 or the object store. The clients in this use case completely skip ZooKeeper. So previously what would happen is a client would want to know, like if you want to do a decommissioning, the client would go to ZooKeeper, it would find all of these things, it'll do all the number crunching, and then it'll say, okay, you're good to go now, there's nothing under replicated, everything is clean, please decommission. Now you don't need to do that, it just simply goes to S3, this is the bookie, these are the ledgers, these are already persisted in S3, nuke the bookie and bring up a new one, and then just point it to that and it will rehydrate from there. So if the client read on the bookie fails and the missing ledgers are also identified, they are also kind of marked and updated and rehydrated back from the object store. So we still use ZooKeeper, but it's for service discovery because that's something that we can't afford to lose. And the metadata requests don't really get affected at this kind of scale. But the new problem here is that we create these reverse maps, right? And we persist them to S3. However, how can we always be sure that the reverse map that we've stored is the freshest one, right? Because we can't be constantly storing the reverse maps. There's that one time delta. Like say you store the reverse map every 1 hour or every 15 minutes, right? What happens in the delta? Like what if something goes wrong? So for that, we kind of revisited at a per bookie level. We introduced another scrutiny, which would understand what ledgers are responsible, what the bookie is responsible for, and then it will store that list at a higher frequency in the object store. So if a particular bookie was to go down, it would just read that and wouldn't have to go to the reverse map. All the metadata operations can go to the reverse map. All the NVMe loss and bookie nuking scenarios can go to this particular snapshot. So yeah. So the result is that we skipped ZooKeeper entirely for frequent client use cases such as decommissioning of nodes, listing of ledgers. We modified the garbage collection algorithm to use the reverse map instead of going to ZooKeeper. And this kind of reduced the total usage of ZooKeeper even as we scale up the bookie nodes to a cluster. So the takeaways here, I guess, more generally are to identify the critical and non-critical operations involving ZooKeeper and offload the data and the non-critical but frequent of those in a new format to the object store and make the client use that instead of using ZooKeeper. So yeah, that's basically the talk. These are our contact details if anybody wants to chat. And yeah, we'll take questions. Thank you.